Thanks, everyone. Thank you, JJ, for having me here. So what I'm going to tell you today is my journey through a number of going from basic science all the way to commercializing technologies. And what I work on is understanding physicochemical interaction at interfaces. Interfaces are everywhere, and that's where a lot of things get bottlenecked, and we are looking at ways to improve efficiency across many industries. So this is a busy slide, but I just wanted to sort of highlight how interfaces play a role across many industries, whether you start in power generation. We worked on improving efficiencies of heat exchangers like boilers and condensers, all the way to thinking about energy-water nexus. And today you'll hear from a startup of mine, Infinite Cooling, where we capture water from these cooling towers. And then a lot of our recent work is on CO2 capture and conversion, and looking at how you can do value products. And then we also, as we are dabbling with some of these, we invented a technology that allows us to actually dispense every last drop of a product, and I'll show how we went from lab to market there. We are working in agriculture, where we are reducing pollution, pesticide pollution by new ways to spray these kinds of things. And finally, we also work in the biomedical space, which I'm not going to be discussing today. However, we're looking at ways to look at the whole bioprocessing value chain and sort of improve efficiency across the scale there. So quickly, as JJ mentioned, we were fortunate to take ideas and then also think about scale-up and manufacturing simultaneously, so we're able to take technologies from lab to market efficiently. So I'll talk about a few of these. Liquid Glide, as I said, is this company where we are able to dispense every last drop of the product. Infinite Cooling, you'll hear from today. AgZen is a pesticide reduction technology. And Alcem is another company where we are working on non-lithium batteries, which are essentially made out of earth-abundant materials, as well as completely aqueous systems. So we call this a green battery, and happy to discuss more if you're interested there. So let me kind of start off. We are surrounded by liquid products, whether it's consumer products like these, which we use daily, or in oil and gas, or in flow batteries, as well as manufacturing, or in the medical industry. And friction between solid-liquid interfaces plays a significant role, and essentially leads to things like drag, so leads to significant pumping costs, all the way to loss of product, or product that's getting stuck inside containers. And so on average, you can see 5 to 10% of viscous products are wasted just because you can't get it out. And there's about 50 plus billion packages that are sold. And all of these are essentially then ending up, the waste that's remaining there can actually fill up, it's a significant amount of waste. All of that waste, for example, can have two things. You think about the CO2 footprint of that waste, and if you cannot get that out, and you think about recyclability in packaging, it's all about, can it be biodegradable? Can you recycle this? Sustainability in packaging is about recyclability. But we should think beyond that. We should think about the product wasted, because that's already a big CO2 footprint of that. Secondly, if you need to you need to clean up these packaging to be able to recycle them, and there's a significant water footprint associated with it if you have product stuck. So and then number one customer complaint is you can't get stuff out of these packaging. So the technology we developed here is essentially a new class of surfaces where we actually develop a composite solid-liquid interface. And what this does is it allows us to fundamentally beat that, there is a scientific fundamental bottleneck, which is the no-slip boundary condition between a solid and a liquid. So we can overcome that and thereby, lead to complete evacuation. And this also gives us a completely new platform to think about surface technologies. It's no longer just a solid film, so it's a solid liquid composite, so you can make it out of materials that are already in the product. For food, we make the coatings out of food. For maybe skincare products, you can make it out of dermatologically safe materials. So it's kind of putting already known materials together in a clever way to have this kind of an effect. So this is sort of a very old prototype where, okay, this is, you guys have the control there. Oops. So this is a very old prototype. When we, so when we invented this work, where we were thinking about reducing friction at interfaces, and we had this, we thought we had a great technology and we want to commercialize, and you can play the next one as well. My wife said, hey, she was trying to get honey out of a bottle, and she said, can you please solve this problem? And then we started thinking about, can we put this in bottles in consumer packaging? And that led to actually making a prototype like this that caught a lot of attention. And we gung-ho went and did a bunch of different products. I'm just going to skip
Who
to
among
this.
us hasn't been guilty of assault on a ketchup bottle, but has technology finally caught up with ketchup?
Look at that thing slide!
Amazing!
Oh my God!
Our long national nightmare is over. Mechanical engineering students at MIT have come up with a super slippery coating that makes anything from ketchup to mayonnaise practically leap out of a bottle coated with the stuff. They call it Liquid Glide. Even Tony Soprano would be beholden to these students. Look how annoyed Tony gets at the dreaded ketchup clog.
And if Carlos starts talking homicide.
Liquid Glide, let it slide. No more banging with shoes or mallets or sucking up kittens.
So the fun thing was, when we did this, we got a lot of people's attention, and my phone didn't stop ringing for 3 months, and we had like 3,000 companies calling us, and we said, okay, this is the right time to start a company. We spun off this technology, and we recently launched with Colgate in this completely new packaging, which is, for the first time, toothpaste has always been sold in these kind of laminate tubes, which is hard to recycle. And for the first time, you have a fully transparent, so you can see zero waste, and you can actually it's a fully recyclable packaging. And so, people are excited about this, and we had a lot of, good reception. This was launched in EU, and led to a bunch of awards in the packaging space, but also in the sustainability space. And then we got a shout out from Trevor Noah, which is always kind of cool. And then it's featured on the CEO's annual shareholder report of Colgate as toothpaste sort of reimagined, and kind of coming up with this completely new ideas in consumer packaging. So where are we taking this? We also are moving to the beauty space. So here again, we're creating every drop platform. The interesting thing is, we can have zero waste. We also think that, there are, this industry has been, these are some other paradigms of this idea, but there's a lot of stuff on things like pumps. There's airless pumps. There's all kinds of, I would say, a lot of claptrap in packaging, which you can, again, hard to recycle, a lot of material that goes into this. I think there's a lot of scope to innovate here. So I'm going to skip that in the interest of time. Again, things like these, where you have thick gels and so on, which are always in tubs or in pretty heavy, pretty thick, jars and so on. You can actually go into a platform like
Many
this,
facial moisturizers,
where you can, don't have to put your hands. It's very hygienic, and yet, you can get every last drop. So we're excited to bring this to this industry. And finally, this is kind of my interesting pet project, which is, if you look at, pretty viscous things like cream cheese here, you have to always use a knife or a fork or some knife to put things out. But you can innovate in packaging here, where you don't have to have all that mess. So there's a lot of interesting paradigms one could think about in terms of consumer packaging. We take this also to manufacturing. The same products that are now being sold, that are sold in packaging, is actually stored in containers like these. This is scaled up now from the small container to a large. This is what, a 500-liter or 1,500-liter tank, I think. And you can see, and this is a pretty expensive beauty product. And you end up with a lot of yield losses. And then when people clean up, you end up with potentially, in some cases, in some industries like paints and so on, you could get wastewater. Here we can dispense again to the last drop, even in a large system. So I think we are excited about this technology because you can do a bunch of things. You can concentrate your product. You don't have to ship all that water everywhere. When product is concentrated, the biggest challenge is getting it out, but we have solved that problem. So we can concentrate. We don't have to ship air. We can create pretty minimalistic and pretty elegant packaging designs and do a sort of a brand refresh. So another sort of a consumer product is fabrics. And here, especially when you're looking at outdoor and waterproofing fabrics, one of the issues has been PFOAs, and these lead to a significant issue, PFAS and so on. So the industry is trying to ban PFOAs and trying to come up with solutions, but it's hard to get hydrophobic surfaces or water-repellent surfaces that are not, don't have those fluorinated chains. So here we have developed, I don't know if this plays, but if you could click on those things. Here we are trying to use new ways to reduce the number of carbon chains, and are able to create very thin films that can meet this sort of challenge, as well as come up with using textures that allows us to now do interesting things with fabrics. So hopefully we can help in this PFAS and PFOA challenge. The water capture stuff, I think you'll hear from my folks later in the day. But I just want to highlight a few things in the energy and the CO2 side. On the energy side, one of the things that we've been working on is, as we know, photo PV market is growing significantly. But there's a mundane thing such as dust that essentially, coats all these surfaces, and you have significant loss in efficiency. It could drop up to 30% if you have this. So how these are lab studies where we have shown that if the efficiency drops quite significantly once you have a layer of dust on these surfaces. So how are these cleaned today? They are cleaned with pretty pure water. I mean, this is not any water. It has to be pure so it doesn't leave any stains or other things. And you're looking at, for example, a 150 megawatt plant. It's 10% of O&M costs, 7 million gallons. You can't dry scrub these because then you'll scratch and do irreparable damage. So this is almost like 30 billion gallons of pure water being used. So the solar industry really needs to think about its water footprint in terms of this cleaning effort. So the question for us was, our challenge was, hey, how can we solve this without using a single drop of water, right? And so, waterless, contactless ways to get rid of these. So the technology we came up with is actually using electrostatic forces. And here what we do is we come up with a new regime where we can, by induction, we are able to get these particles charged and actually repel off of surfaces. And this works pretty much, and we were surprised to see actually a lot of these dust particles behaving like conducting particles. So we can actually get rid of these and create a clean surface. So why does this happen? Most of the dust particles actually are silica, and they can absorb water vapor. And so even in the driest of the deserts, we found that there's enough water vapor in air that it can absorb, and we can apply this technology. And so we figured out why this works, how much charging happens on these particles by doing certain interesting experiments. But we've also shown that we can now, we studied the role of humidity because, as I said, the particles get charged because they are coated with this thin layer of water. And we found that for most desert environments, which are very dry, you can still make this work. And most of these areas also have dew very early in the morning, so that could also help actually get that moisture layer. So long story short is, we can solve this problem of fouling of these panels without using water. And so to prove this out, we actually built a small prototype in the lab. Here is a small robotic arm that moves around, and you'll see that when there is dust, the efficiency of the panel is quite low, or the output, and as we clean, we recover more than sort of 90%, about 90% of the power output. So we have demonstrated this with XY robots, and there's already systems like these that essentially used to scrub the panels. But here, with our technology, we can really do this in a waterless, contactless way. I think I'm going to touch on two topics really quick. On the ag space, what we are doing is we are trying to reduce this amount of agrochemicals that are sprayed. Sprays are the ubiquitous way to deliver crop protection. And here, what happens is large quantities of chemicals are sprayed, and farmers really are in a tight spot. If they don't protect their crops, the bugs eat them, and to protect them, they have to do this. So, and here, significant amount of pesticides are sprayed, and when you look at why so much needs to be sprayed, and what percent of it actually is retained, only 2% or 1 to 5% is retained. The rest of it essentially falls off as and goes into the soils, or goes off as runoff. And that's because a lot of the plant surfaces are hydrophobic, and so to counter them, you make these drops very, very tiny. And when you do this, essentially there's a lot of drift because of this. And so 50% by drift, 50% by because of this issue, you have to spray a lot. And so we've been trying to understand why this happens and how can you prevent this. So you can see even sprays like these, someone is doing handheld, there's so much drift there, and if you don't have protective equipment, people are ingesting this, right? And so this is one of the reasons. And as I said, then it ends up everywhere. You have runoff going off into the atmosphere. I've seen there was a news article a few years ago on things from Idaho coming all the way to New York. So it could be pretty large. It could be field to field. People want to spray in one place and then it could end up somewhere else. So there are a lot of issues with this, but there seems to be no other way to attack this problem. So a lot of illnesses. It's a big market, pesticide market, and then significant contamination of our water streams. So if you look at a regular, a typical farm with $5 million in sales, that's the pesticide that they may be spraying, the spend, and then the margins are low. So these guys don't want to do it. I've realized farmers they're amazing. They're like entrepreneurs trying to do everything with whatever they could get their hands on. But so the question is, how do you reduce that while maintaining the yield? So we studied the fundamentals of how these drops impact surfaces, what's going on, and then we came up with a technology here that allows us to use natural materials, and so that's drops bouncing off of a surface. And here we are basically created additives that are made out of natural materials that can retain the drops better. It doesn't doesn't change the pesticide chemistry or anything. That's whoever the pesticide maker. We improve the delivery. And so what you can see here is these drops that are now impinging actually stick readily. So because of what we are adding. And so we've been able to show, this is in some of the farm studies, we've been able to show 10x reduction in the lab. And then we went and did some more farm studies across a bunch of places. And we've been able to show good coverage with very little use of these things. So these are pictures. We going to farms and working with farmers here in different places. These are some field studies where we were able to retrofit. And at a field scale, we've been able to show 10 to 50% reduction. And also significant, there's a bonus that because of that coverage, we are able to reduce the amount of pests. So my last thing, which I'll try to zoom through in the last few minutes here, is looking at CO2 capture and conversion. So, as a society, we are used to seeing CO2, on the right side of this equation. We burnt fire many years ago, all the way to running airplane or hard to decarbonize sectors like shipping, where CO2 always ends up here. But if we want to put it on the other side, so that we think of CO2 as a resource and what could we do with it, instead of thinking of it as a waste, we need to create a new body of science, and that's kind of what we are trying to work on. And it's important to do all kinds of capture and conversion, but we definitely need negative emission technologies, so as to take CO2 out of the environment. And here, this is something that probably all of you know, so no need to belabor on this. For example, something like shipping, here, a average 50 megawatt engine ship will produce about a ton of CO2, per day. So how do you deal with this thing, right? And or we have to stop shipping completely, which is not going to happen. So how do you meet this IMO timeline to be emissions free? So what we are doing in my lab is kind of looking at all these different sources of CO2, whether it's in point source, air, or in oceans, efficient ways to capture, and also think about conversion. And in the conversion, we do upcycling, we do mineralization, we also use biological ways to convert it into value products. And then, so two projects that I want to highlight here are this ocean capture work, which I'm working on with Professor Alan Hatton in chemical engineering. The interesting thing with oceans is there's already a lot of CO2 that's absorbed in the oceans. It's 100 times more concentrated than air, and so the capture step is already kind of done. And there is an interesting sort of I would say, a carbonate-bicarbonate equilibrium that allows for, by changing this proton concentration, you can release the CO2 from the oceans. So what we've been working on here is a system that allows us to change pH or swing the pH in one cell, acidify, release CO2, and capture it in another cell, release, and then we again realkalize it and put it back into the ocean. So we've been able to show that we can, at a bench scale, we've been able to show how to optimize this. I think, let me just jump forward here. So this is a cell 1 where we increase the pH and release CO2, and cell 2 where we can put the bring the pH back up. So this almost is super energy efficient because it almost works like a battery. We are not, splitting water. We are not using expensive membranes or things like that. And so our goal here is, we are at this. We are right now maybe at in this kind of a zone, and we want to be able to get to less than $100 per ton of CO2. And finally, you have all the CO2, great, what do you do with this thing? We've been looking at ways to do conversion by different steps. I'll highlight some work we are doing on the electrochemical processes. You can go from CO2 to products such as these, and of these, what makes sense is actually having ethylene from a techno-economic point of view. But one of the key challenges is you need to get CO2 into an electrolyte and then be able to do the electrocatalysis. So this interface here plays an important role. And if you don't design this system very well, you end up actually, instead of producing products, you end up producing, doing water splitting. So we've invented ways that allows us to actually improve the CO2 electrolysis and not have hydrogen evolution by actually supersaturating the environment in the electrolyte with CO2. But that's not enough because we are still at very low current densities there. And if you look at the techno-economics of this, we want to be at pretty high current densities. We want to be able to get into something like an amp, like 750, close to an amp per centimeter square. And if you're able to get there, ethylene, for example, makes a lot of sense because of the market size and how much CO2 is actually coming out of ethylene crackers and so on. So I'm almost towards the end of my talk, but what we are trying to do here is come up with these new reactors that allow us to beat this challenge in the CO2 conversion space, which is a trade-off between conductivity and sort of current density. And we are trying to kind of get to this space. And we already, with our new technology, we are able to show that we can, conventional electrolyzers, we are able to become more efficient. We created a test bed where we are able to scale up. We are focused on robustness and scale, really, because there's a lot of materials out there, but really making it robust, work 24/7, is a key to making some of these happen. And finally, I think what I want to end on is in the whole carbon capture space, you have capture, then you have to extract the CO2 and do something with it, whether you put it in ground, mineralize, or so there's a conversion step. But we are focused on doing this in an integrated way where we can capture and then convert in the same space. And one of the schemes that we are using is based on some of the technology where we can capture mists and so on. We can use much better capture means by using droplets, but they get entrained, but we have a technology to capture them. And that allows us to do this no matter what the source is, and then essentially, it could be either stripped or it could be converted using our conversion approaches, the reactors that we are kind of building. So I'm excited about this idea, and this is kind of how you'll see some of this today, but this is how this mist capture works, where we have this mist, and by using electric fields, we can make those go away, and we can actually collect all that. And now this could be used, the CO2 dissolved in this, and you could use it to do the reaction without, again, having to remove and add an additional step. That takes up significant amount of energy. So I'll end here, and we're working on other things like efficient hydrogen electrolyzers and so on, but I zeroed out here on the time, so happy to take any questions.
Wow, so thank you so much.
Shows you what a broad range of things and they all go back to exploiting and leveraging fundamental science from your lab. So let's look at some of the questions. I know you covered a lot of topics, so I think many of the questions were driven by what you talked about first. And I think they were talking about the life cycle analysis of like the coating. How does that compare? And is it recyclable? Is it GHG friendly, economical, things like that?
Yeah, no, that's a great question. Yeah, we've always been thinking about this, from fundamentals, thinking about the life cycle analysis, the life cycle impact, as well as the sustainability impact, and therefore, I can go into details, but I don't have time. Yes, we have done those, and we've looked at the product wasted is so significant that it can actually have, by this super thin layer of the material that we are putting in, this is just microns thick. You could take, I could take this cup of this much material and coat maybe millions of packaging, right? So there's a significant savings there, both on the product side, but also on the on all the emissions and other things.
Okay. So another question, I think a lot of the ones are dealing with the Liquid Glide coating, and a lot of information is out there on your website and the Liquid Glide website that would answer some of those. Yeah. So I want to pivot to, we have time for one more question, I think. The question about electrostatic cleaning. Mm-hmm. Does it work on other than dust, like bird dung? Does it work on complex shapes or flat surfaces only?
Oh, yeah, it can work on complex shapes. There's no issues with that. We are working on, as in the current embodiment, that works with granular particles. We are working on ways to combine it with other means to also look at very sticky, soft kind of materials that are quite sticky. So that's an ongoing piece of work in the group. Okay.
So with that, I want to just pause here. I know we have a lot more questions, Professor Varanasi, but we're running into our break time now, and we have an already short break. So Right now, we're going to take a break until, oh, you have 3 more minutes? You're going to let it go? OK. Let's go back to the questions and see if another one we can field. So a lot of them are about the coding. So maybe you can say a little bit about the codings with respect to PFAS and that kind of application.
Oh, there, yeah, I think what we are looking at basically C6, which is kind of where the industry wants to go. And we've been able to show that. We've been able to show durability or number of wash cycles as well, because ultimately you can have this if it, you wash it once and it goes away, that's a challenge. So the bottom line there in the waterproofing world is there are no good solutions when you go to these low chain kind of polymers to do to provide hydrophobicity, and that there is surface chemistry, but then you could also play with surface morphology, and so by using both of them, I think we can get to pretty good solutions, and yeah. And those, if you're less than C6, those basically can biodegrade and won't stay in the environment like the PFOAs and others. So that's one way. I'm hoping that there'll be more solutions in that space.
Okay. How are we doing? Oh, one more minute? Okay. Let's see. I'm trying to see if there's any questions that come up related to the carbon capture ideas.
Yeah, I just went so fast in the end. Probably.
Well, let me.
Oh, I can answer. Does Liquid Glide have PFAS? No.
Right.
It's made out of, for example, the toothpaste surfaces that you saw. They are all made out of materials already in the toothpaste, for example, or the skincare made out of all the dermatologically safe materials. It's that platform of using combination of solids and liquids allows us to do that. So, yeah.
Okay. So with that, thank you so much.
Yeah.